Just like how when we first learn integers or just any kind of base numbers, we start looking at operations on these things like addition, subtraction, multiplication, division. And like how when we first learn fractions, we learn addition, subtraction, multiplication, division of fractions. Here we have functions, and we can start learning what is the addition, multiplication, division, and subtraction of functions. There's also a composition of functions, which we'll talk about. They can be composed and combined to make new functions. Sometimes these operations change the properties of these functions. And we've talked about many different types. Now we can create new ones by using these operations. So first off here, let's talk about some basic function and basic properties and how they can change when you do these operations on them. This function right here, this is 2x squared plus 5x to the fourth power minus 1. This is a polynomial function, and it is a polynomial of degree 4. That's the highest power, so that's the highest degree. So it follows that kind of behavior of a fourth degree polynomial, and you'll see how it just shoots up like this. Now, polynomials all have very similar behavior. Odd and even polynomials have slightly different, but they always have the same kind of properties, namely their domain is everything. Now, it may not look like all of this stuff is within the domain of this function, but I can zoom out far enough and eventually this thing will cover all of these values. It's just going to be very high. Okay, playing around with a little bit, we have this is the same function, and I've just adjusted the scale. You see, we're going from -10 to 10 and going from like -5 to 10 here. And it looks like this stuff and this stuff are not within the domain of this function because it doesn't cross over it. But if I start adding zeros, now you see it's going over a little bit more. Add another 0, it's going over even more. And I start adding a bunch of zeros, and you can see it definitely does cross it. In fact, I could keep zooming out. And we'll look at this thing and just add zeros to it. And you see it definitely eventually crosses it. It has to go up to very extremely large numbers. This is 10 billion, I think. So it's very large numbers, but you will eventually cross it. And all polynomials work this way. They have domains from -infinity to +infinity. I could zoom out as far as I want. Zoom out very far, and this thing looks very thin. And all I have to do is change the scale to get us to where we want. Like this is going to be adding another 0, adding another 0, another. You keep going, and eventually you can cross it. At some point it does cross. Okay, let's go back to the home scale. Oops. There we go. And move on to the next type of function. So this is a polynomial. Its domain is -infinity to infinity. And this one's range, you can see it hits here at -1 and goes on up to infinity. Now let's look at the next one. This one is called a rational function. That's because there's a division there. It's a polynomial divided by a polynomial. And you see that it has this interesting behavior here where it has this kind of jump. It goes off down to -infinity this way, and then it jumps to +infinity and goes off that way. And this right here, this area right here, is called an asymptote. And what I can do, you can see it's on -5. What I can do is say x equal to -5. I'm going to make it red in color. And you'll see that this line gets close and close and close. It looks like it's touching it, but you zoom in enough and it's not. And you can keep going up and keep going up further and further and further, and it'll keep getting closer and closer ever slowly. But it will never cross that line. That's what an asymptote is. And the same thing is true for this bottom part. So this function, you can definitely see how it goes from negative infinity all the way on up until this point right here. In fact, negative 5 is the only x value that this function does not ever have in its domain. That's because there's an asymptote there. But it does have everything above it and goes on off to positive infinity. You can also see that we have a range of negative infinity on up to, well, this is also an asymptote. This line gets ever closer and closer to the x-axis, but it never touches it. It's getting closer and closer and closer. The same thing is true with this side. It gets closer and closer and closer, but never touches the x-axis. That means 0 is excluded from the domain. From the range, but everything else is included. Just to briefly show you what I'm talking about here. The domain of 2 over x plus 5, the domain of this will be from negative infinity up to this point right here. That's where the line does not cross, or the graph does not cross, so negative 5. Union with negative 5 up to infinity. The range goes from negative infinity to 0, union with 0 to infinity. So the only thing that's removed from the domain is this negative 5 value. The only thing removed from the range is the 0 value. Here's our next function. It is this kind of long, weird thing. It's still a rational function, but there's this another rational function inside of it. This is actually a composition of two rational functions. And you see we have very similar behavior to the previous one. The previous one we had was this. You see how it has those asymptotes. This one also has that asymptote behavior there. What's interesting, however, is Desmos specifically makes a point of this point right here. Now this point is interesting because it looks like it's the x-intercept. However, this is not actually within the graph. That's because when x equals 2, we have 2 minus 2 is 0 in the denominator here. And that gives us 0 in the denominator. We can never divide by 0. And so we must exclude that value from our denominator. Also, this asymptote here happens when this entire denominator equals 0. I just want to show you the reason why we have two different things. So 1 over 4 over x minus 2 minus 3. We need to worry ourselves about if this thing equals 0 and if this thing equals 0. So x minus 2 equals 0 when x equals 2. And we have a 0 in the denominator when 4 over x minus 2 minus 3 equals 0. Add 3. I'm going to multiply by x minus 2 to both sides. We have 3 times x minus 2. Distribute that. Add 6. And then divide by 3. So we have x equals 10 over 3. And that's what this line is here. I can show you that quite easily by just saying x equals 10 over 3. You can see that line crosses straight through. Make it purple. The line crosses straight through that asymptote, and you can see that these things get closer and closer to this thing, but never cross it. That's because we have this whole thing becomes 0. And then we have this special point here at x equal to 2. There's actually a hole there. So it's going to look something like this in the graph. We have a graph that looks like this. It goes to up to 2 here. This is 2. There's going to be an open dot right there. Desmos doesn't show it because everything around the 2 is included. Right? You can get closer and closer and closer. Everything all the way on up to 2. That's all included. But 2 is the only excluded variable. That's why they have a dot there. All right, the next one is the square root of x. We've seen this one before. Square root of x looks like this. What's the domain of this guy? Well, we see all of the positive, right? You can keep going over and over. All the positive x's are included. What's interesting though is that it kind of just comes to a stop right here. And it looks like it goes right to 0. Does it include 0? Well, it's actually quite easy to check. What is the square root of 0? The square root of 0 is 0, and that is a real number, so that's fine. Anything that is to the left of the 0 is negative, and any of those things, if you put those inside the square root, you get a complex number, and that cannot be graphed on this real number plane. So we have to exclude those from the domain. Therefore, anything that is less than 0 is excluded from the base square root function. This is actually the parent function of the square root family. And x plus 5, you see, this is just a shift over 5 units. That's because it's a plus 5 on the inside of the function. A plus or minus is just a shift. And since this is a plus 5, it's going to be a 5 shifted to the left. And we can see the domain of this function now is any x greater than or equal to negative 5. Negative 5 plus 5 is 0. The square root of 0 is 0, so it's fine. Anything to the left of that gives us a complex number, so we must exclude it. So that's square root function. Let's look at a cube root function. Now this is interesting. You see that it has this side of it, but it also has this side of it down here. That's because a cube root function can never get a complex number as a result. If I plugged in, let's see, yeah, right here, negative 6. You can see this value right here crosses negative 6. I can't get it exact. I had it there for a second, but if you plug in negative 6 into here, negative 6 minus 2 is negative 8. And the cube root of negative 8 is negative 2. You can see that negative 6 goes to negative 2. That's because negative 2 times negative 2 times negative 2, 2 negatives cancel. We still have a single negative, and we get negative 8. So a cube root function does not have any issues with negatives. It doesn't have any issues with positives. It is actually completely defined on the entirety of the real number line, so negative infinity to infinity. And all of these functions, right, it stops here for these cube root functions, but it goes on up indefinitely. Just like this first function here, you can eventually see that it goes out. Well, this one can also do that. We can go out far enough this way, and it'll keep going off toward positive infinity that way. And the cube root function goes off towards negative infinity that way. So these two things have a range of 0 to positive infinity, including 0, since 0 is included right there. And this one, this cube root function, has negative infinity to positive infinity for its range, since it can touch everything. We talked about domains a little bit. Now let's actually do the arithmetic. So here I have two functions, f of x equals 5x plus 2 and g of x equals 3x minus 4. And these functions are linear functions. So let's add them up and see what we get. F of x is 5x plus 2. Put that in parentheses, plus g of x is 3x minus 4. Of course, the parentheses here don't mean much. We can actually just drop them and add like terms. 5x, 3x, 2 and negative 4. That gives us 8x minus 2. This is just a linear function. It's just a line. And you'll see that the domain of this is going to be negative infinity to positive infinity. It's actually considered a polynomial as well. And all polynomials have the same domain. Negative infinity to positive infinity. All right, 5x plus 2 minus 3x minus 4. This should be the negative. Gives us 5x plus 2 minus 3x plus 4. And combining like terms gives us plus 6. This is again a linear function, so its domain is negative infinity to infinity. You can of course just graph these things, and you'll see they cover everything, all of the x values. Okay, now we have multiplication, which is fine. We're going to FOIL this thing out. 5x times 3x is 15x squared. 5x times negative 4 is negative 20x. 2 times 3 is plus 6x, and 2 times negative 4 is negative 8. Combining like terms gives us 5x squared minus 14x minus 8, which is a quadratic. It is a power of 2, so it's a quadratic function. This is just a special polynomial. Polynomial still has negative infinity to infinity. Okay, last one is division. 5x plus 2 over 3x minus 4. There's nothing to factor. There's nothing to cancel. This is the best we can do. And this is a rational function. It's no longer polynomial, it's rational. The main concern with rational functions are when is the denominator equal to 0. All I have to do to find that is set it equal to 0. Add 4. 5 by 3. So when x equals 4/3, we have a division by 0. So we must say x cannot equal 4/3. And that means we have this as our domain set. It's the only issue there. The 4/3 is where that horizontal, or sorry, vertical asymptote would be. That thing that gets ever closer and closer to it, but never crosses that line. That's what that 0 denominator gives us. Now, what we've done here is arithmetic with functions. We also have composition of functions. Composition of functions is just where you plug in one function to the other. So let me take these again. And now let's look at function composition. So f of g of x and g of f of x. So in the first one, we're plugging g of x into f of x, or in other words, into the x value. So f of g of x is going to be 5 times x, which is 3x minus 4, plus 2. 5x plus 2. 5x plus 2. That's all I've done there. And we can simplify. 15x minus 20 plus 2. 15x minus 18. This is a linear function. It has the domain from negative infinity to positive infinity. Okay, g of f of x is where we plug in the other way. I'm going to take this thing, plug it into here, which means plug it right into the x variable. So g of x is 3x, which is now 5x plus 2, minus 4. Distributing it in there, we get 15x plus 6 minus 4, 15x plus 2. Linear function, negative infinity to infinity. That's function composition. All right, here I have some more functions to look at. Hopefully I'll have enough room to do all this in one page. So here our functions are m of x is the square root of x, and n of x is x plus 2. The previous ones we had two linear functions and they combined nicely. This one's not going to be the same case. Here we have two different functions, a square root and a linear. And so a lot of times, like for instance this first one, we have the square root of x plus 2. There's no simplification I can do there. The square root of x does not combine well with anything else in there. So this is the best we can do. Now, what's the domain? We kind of look at each part and consider the domain of each of the functions. So first off, we have the square root of x. This has a domain of 0 to positive infinity, including 0. And the next part here, x plus 2, this has a domain of everything. You must look at the more restricted domain because that's where we're going to have issues, right? We could plug -3 into there, but we cannot plug -3 and graph it into there. We can do it, but we have to consider complex numbers, and that cannot be graphed on the real number plane. So we have to exclude that from the domain. Therefore, this domain is from 0 to positive infinity. It takes the more restricted domain. Okay, the next one is the square root of x minus x plus 2. Of course, we can distribute the negative, but nothing really happens more than that because, again, we cannot combine the square root of x and x. They're not like terms. And this thing, in fact, has the exact same domain. Nothing really has changed. The minus x minus 2, that's just a linear function. It has everything in this domain, but the square root of x is very restricted. Okay, the next one is the square root of x times x plus 2. Now, the square root of x is going to be x to the 1/2 power. And so we get x to the 3/2 power plus 2x to the 1/2 power. Now this one's a little weird, and it might take you to graph this. Let's look at that real quick. Okay, so I've graphed the function that we've looked at, and it has this weird little kind of motion inward, but then it kind of comes out, and then it seems to go like this, exaggerated. Like kind of go like that and like that. It's like a weird ass shape. But it definitely looks like it stops here at 0. And we can test that by plugging 0 into here. 0 to the 3/2 power, well, 0 to any power is 0. 2 times 0 to the 1/2, that's going to be 2 times 0, which is 0. 0 plus 0 is 0, and that's a real number. So 0 is included here. Anything negative, however, gives us a negative in a square root, which means we have a complex number. So we can immediately disregard that. And it looks like everything positive works. And that makes sense. If you plug this into a calculator, any positive number, this will give you a positive number as a result. So the domain for this one is going to be from 0 on up to positive infinity. Okay, the next one, square root of x over x plus 2. There's really nothing else we can do here. Now this one has two things we must consider. We have the square root of x, which we know has 0 to infinity as the domain, and x plus 2. X plus 2 is in the denominator, which means we must exclude when x plus 2 equals 0. Subtract 2 and we get x equal to -2. X cannot equal -2. Now, however, x equal to -2 is not within this original domain. So that number is already excluded by our square root functions, restricted domain, which means the domain is square root of x from 0, including it all the way up to infinity. That's all we have to consider. Now, the next two are composition of functions. M of n of x, that means we just plug this one into the other function. So we have the square root of n of x, and that's it. This is a shifted square root function. It's shifted 2 units to the left because it's on the inside. That means it's going to be left or right. And this is positive, so it means it shifts to the negative direction because it works backwards on the inside. Okay, you can always just graph this and you'll see it's 2 units shifted to the left. That you can also just check where is 0 on the inside. That's when x equals -2. When you plug -2 into there, you get -2 plus 2 is 0, and the square root of 0 is 0. Anything to the left of -2, for instance, -3, -3 plus 2 is -1, and the square root of -1 is I. So we have a complex number, so we must exclude that from the domain. So we know that this thing goes from -2 up to infinity, including -2. It's just the same thing as the previous domains, as actually really all the domains, but we've just shifted it to the left 2 units. That doesn't, of course, shift the infinity, because the infinity continues infinitely. But it does shift the 0 left 2 units. Okay, now for the other composition, plugging in the square root of x into x plus 2, which really just takes this thing and plugs it in right there. So we have the square root of x plus 2. This is really just a square root function that has been raised 2 units upward. This is on the outside, so it's going to be a shift up or down, and it's a plus, so it's going to be a shift upward 2 units. Now that does not change the domain. Because it's a shift vertically, it does not change the left or right domain values. So we know it goes from 0 to infinity.